Okay, so I'm going to talk about missing and maybe future C++ range concepts. So just like my colleague who spoke here before, I also work at compcile. We are the world's leading business presentation software. We were founded in 2002. We have over 1 million users at 25,000 companies. We sell a plugin that seamlessly integrates into PowerPoint that makes it just easier to create presentations and charts and stuff like that. So if you have to do so many presentations, we are sort of like the market standard for that. This is done by reverse engineering, so we essentially hack into PowerPoint, and then we have fancy algorithms to do automatic layout and that sort of thing. We do everything in C++, and we also heavily support the C++ standardization process. And at the core of our product is the compcile standard library. It started out as some sort of just some couple extensions to boost and the standard library, and it is heavily built around ranges. So it predates std ranges and range tree 3, sort of started evolving out of boost ranges, but now it's entirely different. It is similar to Flux in that we use cursors. I'm not sure if you're familiar with that. Not important for this talk. But unlike Flux, we use that only as an implementation detail, so the main interface are still iterators. It's partially public, and I already gave a talk about it 2 years ago at C++ Now to present some general principles. In this talk, I will focus on missing range concepts that we have implemented in the compcile library, which I think would make sense to have in the standard. Our implementation is constrained by the C++23 subset that is already implemented by MSVC. However, for convenience, I will use all C++23 and C++26 features just to make the slide code a little bit nicer. But in principle, all of this has been implemented using C++23. I will also pretend that everything is in the std ranges namespace, so I will just use the equivalent functions from std ranges instead of our own ones, just so you don't have to be familiar with that. And even though I'm now officially chairing the study group in the C++ committee that standardizes std ranges, I'm not promising that any of this actually makes it into the standard library. Just because I'm giving a conference talk about it, there's a bit more work involved with that. And also other people have to agree that that is useful. And even though I'm sharing, I can't. I got the paper rejected that I wrote last week in the group that I was chairing. So I have 2 problems. The first problem is optimizations for better performance. The second problem is metaprogramming for compile-time-magic. This is the part Matt is here for. And then if you're still here after that, we can talk about some unresolved standard issues in the wording of the ranges specification. So it's truly something for everybody. So for convention, I will use stdview for std views and stdr for std ranges, and then potentially future extensions are in std2v and std2r, just for presentations. So let's begin with the first problem. The example problem I came up with is we want to read a file and we want to normalize all tab characters to 4 spaces. And this can be somewhat trivially done using a range pipeline. So we first read our file, and this returns a range of all the characters in the file. And then we transform each character. If it's a tab, we turn it into 4 spaces. Otherwise, we keep it unchanged. And we're returning a std string here, but it all fits in the small buffer optimization, so we don't do any allocation. And this is just the most convenient way to turn a single character into potentially a range of characters. So I'm just storing them in a string. The result of transform is a range of ranges, so a range of std strings, but we want a range of characters, so we join them all back together using join. This flattens it out. And then we have a lazy thing. We want to eagerly turn that into a std string, so we call std ranges2. It's a C++23 thing that takes the entire pipeline and constructs the appropriate container out of it. The only thing that's non-standard is the read file function. So the read file function takes a path and returns an input range. And the core implementation looks something like this. So it's based around iterators. And the iterators, we maintain a buffer of characters. So we don't want to call the file API function for every single character. So instead, we have a buffer. The dereference operator of the iterator just returns whatever character we have in the buffer. And then we increment it in the increment operator. And if we reach the end, then we will read more, fill the entire buffer, reset the pointers back to the beginning, and continue iterating. This is a nice way to turn a file into a range. Now, the first problem we have, this is actually something that's in the standard. I just wanted to mention it because I think it's pretty cool. And this is approximately sized ranges. So what we do at the end is we're calling std ranges2 into a std string. And if our range is sized, this is very easy. So we create an empty string, we allocate enough space for it by just asking the range for the size, and then we just copy all the characters from the range into the string, and the end result is a string that contains all the characters. If we're having a forward range, then we don't have a size, so instead we call distance. And what distance does, it iterates over all the characters of the range, and like we just count them, and this gives us the size, and then we call reserve. And this is still more efficient than having the eager like reallocation every so often. So this is presumably what the implementation does. But if you're having an input range, then we cannot do a reserve, because an input range can only be iterated once. And when we iterate over it to compute the size, then we can't iterate over it again to get the actual characters. So we can't actually reserve. This means we have to do the frequent pushbacks. And this is what we're having here. Even though read file is an input range, and we can make it a sized input range, because we can just query the file system for the size of the file, after the transform and the join, we have something that is no longer sized. Because the transform turns it into a sized input range of sized ranges, like one string for each character, and each string is sized. But when we join them back together, we have to sum all the sizes of the individual strings, so we don't have a size overall. So we lose size information. And this makes sense, because we like expand tabs into spaces, and we don't know a priori how many tabs there are in the file. Right? But let's say that most of the files we deal with, they do not contain any tabs. Right? Because we are like nicely formatted files, nobody put in any tabs in there. And so this function doesn't really need to do anything. And it would be nice if we could like propagate this approximate size information, right? If you could propagate and say that, hey, after the join, we have approximately the same size as the input range. And this is where the approximately sized range concept comes in. So if you have an approximately sized range, you can call this function reserve hint. And this is a C++26 thing. So we can call reserve hint, and this returns a hint that we can pass to reserve. And then we can implement ranges too by calling reserve hint. It's a bit unfortunate that the concept is called approximately sized range, but the function is called reserve hint. It used to be called approximate size, but then somehow in the standardization process, one of them got renamed, but not the other. Let's see what we can do about that. I think it's confusing. And this reserve hint function, this essentially does one of these things. So if the range is sized, then it is approximately sized, and we just return the size. Otherwise, we call reserve hint as a member function or as ADL lookup. And then the views, they propagate approximate sizeness. So like views like transform or reverse or take or drop, they all have enough information to compute the approximate sized. So if your input is approximately sized, the result is also approximately sized. But crucially, join doesn't do that. Because in general, join can't, right? There is no inherent relationship. But in our specific case, we know that we could propagate the approximate size. So we just need a facility to do that. So we could imagine a very simple like wrapper that just wraps an input range and also stores an approximate size, and then we just use that as the reserve hint. And then we can construct our approximately sized range. So we create the pipeline before the transform, and then we pass that size to the approximate size, and then we join that together, and then we turn that into a string. And this works. It's just a bit ugly, because we have to like put the range into like a single variable because we're using it twice in there, and we really break this nice pipeline. We can give it a slightly better interface by introducing the approximately unchanged size range adapter. And this just says, okay, so we take the input range, we join it, and this doesn't change the size. Right? And then it's like more nice and elegant code. And the implementation for that, it's a bit technical. We need to have like a range adapter closure object. The whole pipeline thing is a bit messy and produces bad error messages. And this really should be a language feature. But the idea is we've got this thing which takes the join as a constructor argument, and then we remember that. And then we have the call operator, which takes the input range, and we pass its reserve hint to the approximately sized thing, and also forward it to the closure. And this does what we want. It's just a nice, bit weird functional stuff that takes a while to figure out. I just got a job offer. Anyways, impressive stuff, apparently. Should let me disable email notifications. Because this is like, it's going in so much nicer, and I don't want to be flooded. Anyways, I really like my job, just for the record. Yeah, there's nothing. We're also hiring, so. Okay. Something that is actually missing from the standard library. generators. So this is the code we have. I'm going to ignore the approximate size stuff for the rest of the talk, just for space issues. So this is the code that we have, and it essentially does this imperative code. So we're having an infinite loop where we, like if you were to write this imperatively, this is what you do. So if this read more function that reads stuff into buffer, you then get this buffer. If you're done, then you break out of the loop. Otherwise, you iterate over each character in the buffer. You translate that by turning it into a string, translate over each character, and then you do something with it. In this case, we want to turn that all into a string. And this is the equivalent imperative code that will do the same thing, right? So the first couple lines, this is the read file, and then the loop with the function, this is a transform join. Now, what does the actual ranges code do? Well, we have iterators. So the iterators have state. For the join iterator, we are having, so essentially we're having the current outer iterator, and then an iterator into the current element of the outer range. So we have two iterators, one that advances over the outer range, and then the inner one that advances over each element of the outer range. The transform just doesn't introduce any additional state besides the function object, which I'm ignoring here, so it just grabs the base iterator. And then the read file iterator has the 2 pointers. The dereference operator for join is simply decrements the inner, dereferences the inner iterator. The one from transform, it forwards to the base, but through the transformation function. And the one from the read file also just reads from the buffer. And the interesting logic here is in the increment. So for join, we increment the inner iterator. If this reaches the end of the current element, then we skip over until we find the next non-empty range in the outer one and start producing elements out of this one. So we reset inner to the beginning of the next element in the outer range. Transform just transforms, increments the underlying iterator. And a read file iterator does something very similar to the join one, it increments the element in the buffer, and if it reaches the end, we reset the buffers to the next element by calling the readmore function. So in the imperative code, we just have nested loops. But with the iterators, we've got the state machine, where we split the nested loops into a read step and an advanced step. And then we have arbitrarily deeply nested state machines in there, right? The join, this is just 2 loops, but they're not represented as 2 loops. Instead, we've got extra logic in the increment, right? And this means that iterators inherently have some overhead, right? They're not directly the nested loops, they are the state machine. And for performance, the optimizer has to recognize that they're nested loops, does all a bunch of inlining, and unroll the state machine. So we will inherently have some overhead. And stuff like join are particularly problematic, because join is just 2 nested loops, right? But instead, we've got the state machine. Concat, this concatenates multiple ranges, and this is logically just n ranges in sequence. But instead, the actual implementation involves a variant of iterators, and then we advance the currently active one, and if this reaches the end, then we change the variant to point to the next iterator, and there's this is famously very involved. And then transform and filter, this is logically 1 loop with an if, but instead we've got the state machine, which potentially has to semantically do something that invokes the transformation function twice, once in the decrement and once in the dereference and once in the increment. And so this is not efficient. So why do we have state machines? Well, we have state machines because ranges have a pull model. In a pull model, the range consumer is entirely in control, right? So you can have a range, you can get an iterator, and then you can do whatever you want with it, like read 1 element, skip 1, use 1 element twice, skip 2 elements, use it again, and then we stop at this point and no longer want to continue iterating, right? The consumer is in full control. However, often this is completely unnecessary because you're just calling something like for each. And in this case, you don't want any control, you just want give me all the elements, right? So we don't need control, yet we have it. And every time we have a range-based for loop, we just use a regular range-based for loop. We represent the range by a potentially very complex state machine, and then this state machine is repeatedly advanced until completion. So the entire thing is a bit unnecessary because we don't need the state machine, and yet we construct one and then just exhaustively enumerate all the states. So better for this particular case is a push model, because this one directly expresses the loop, right? Then the range producer is the one in control, because the range eagerly pushes value onto the consumer using a function object as a sink. And the consumer just gets the values and has to do something with it. This is what you do in for each, or in a range-based for loop. You just get values and you do something with it, but you're not really in control over when you get them or skipping elements and stuff like that. And what would be really nice is a direct customization of the entire loop, so we don't need to express a loop as a state machine. I had a paper for that together with Barry a couple of years ago to just say, okay, maybe we can like customize the range-based for loop by having a customization function that takes the body of the for loop as a lambda, and then we pass that on, and then we just invoke the lambda for all the values. This was unfortunately rejected, and since then, Barry, who worked on the reflection papers, has written a blog post on how you can do that with his like reflection macros. So the nice thing about C++ is you don't really need language features. You can just build them with other language features. But this is like still in the future. This is relies on token injection, which isn't even part of C++ 26 yet. So I think so. For this, we have a pure library solution. Essentially, it's something like a for each while customization mode. This takes a range and a sink, and it iterates over the range and calls the sink for each element as long as the sink returns true. And the default implementation just uses the range-based for loop, right? This is the default implementation. So we iterate over all the characters or elements of our range and call the sink. And if the sink returns false, then we propagate that through and continue stop iteration. Otherwise, we continue and return true at the end. However, it's a customization point, so we can provide better behavior for some ranges. For example, for our transform view, we just implement, okay, so for each while on transform is just for each while on the base range, but then we don't invoke the sink directly. Instead, we pass each element through to the transformation function, right? Because this is what the transform does. It just changes the elements a bit. Or for a join, well, a join is two loops, so we write two loops, right? Like one loop over the outer range, and then one loop over the inner, each element of the outer range, and we pass that one to the sink, right? So the end result is that we get each element joined together, but we just wrote two loops instead of the state machine. And for our read file view, we can just write the imperative code directly, right? You just read the next buffer. If the buffer is empty, we're done. Otherwise, we propagate each element of our buffer to the sink until the sink returns false, right? And that way, we can directly express the loops without having to involve any iterators. And so we can then use this customization point in algorithm implementations. Like algorithms like for each, copy, transform, they're all essentially loops. So they can all be mapped directly to for each while instead of the range-based for loop, so they can completely avoid any iterator override. And then we also have the short-circuiting loops. Luckily, the sink can like also stop iteration, so we can also implement stuff like all of or equal or contains, which iterate until something changes. And then we just return false from the sink, stop iteration, and we have that. And so if we were to use for each while to iterate over the range pipeline instead of the iterator one, this happens after one level of inlining. So the join is the two nested loops. So after one level of inlining, we get the custom implementation for join with the two nested loops, one over the outer range and then over each element of the inner one. If we do another level of inlining, we inline the inner for each while. So the for each while over a string, this just uses iterators because that's the most efficient way you can do. So we just get the default implementation. If we inline again, we inline the transform stuff. So we now iterate over the base of the range and still have to do the transform, so invoke the function on each element. And then if we inline again, the base of the base is the read file, so we get the for each while code of the read file code. And what we end up with after a couple of inlining is just the imperative code. So the transformation from the iterator state machine to the imperative code is non-trivial, right? Optimizers to see a lot of things. But with for each while, it's just inlining. And compilers are really good at inlining. That's like the most important optimization. And just by repeatedly inlining small functions, we end up directly with the imperative code, and so don't have any iterator override. Now you might ask yourself, well, if you want to express loops using like ranges, like why not use the generator and coroutines, right? You can just write a function that returns a generator, and then you can just write the imperative code and yield each element that you want. However, this doesn't solve the problem because coroutines are still state machine. Instead of just you having to write them, the compiler writes them for you, right? It's still the pull model. This is the entire point of having the coroutines, that you can stop at any point, right? It's still the pull model, not the push model. And in addition, we also have like overhead like heap allocation that wouldn't be present with the iterators. So maybe coroutines are better because the compiler generates the state machine and then it can nicer see through that. But then we also have overhead like heap allocation that needs to be alighted, right? So if we want to do this with coroutines, we need better optimizations for the generator to have something like the push model, a mode for the push model for the generator. And this is sort of the unfortunate thing if you got stuff with natural syntax but bad performance, right? So for each while is the equivalent of co-yield. Co-yield has a natural syntax but bad performance, and this is similar to having senders, receivers, and co-await. Like co-await has nicer syntax, but it has worse performance, so we ended up with a library solution for that as well. Now, of course, if you want to optimize the ranges using generators, like it's not all that simple. Like you don't just add the for each while customization mode and use it and you're done. There are like complications. For example, what about reverse, right? Reverse is also just a loop, but it goes backwards. So maybe we need like a second customization point to go backwards. We have that at think-cell, so we have for each while reversed, right? And then most algorithms implement both of them, and they just forward to the reverse version in the reverse case. But this is like a lot of complexity. Then we have zip. So zip is a view that takes a bunch of ranges and iterates over them in lockstep. So if you zip like an index sequence and a container, you get each index of the container together with its element. But we can't implement that purely in terms of for each while, because with for each while, you can only go over one at a time, right? So you can only use for each while on one of them, and the other ones have to use iterators, because this is not implementable otherwise. So there is some heuristic which one should use the for each while, because if you have like a concat and a span, it doesn't make sense to have the for each while implementation for the span because the concat one is the more expensive, right? So you want to use the for each while for the concat and then just use iterators to iterate over the span. And so we have some heuristics to pick for zip which for each while implementation we use, right? Which adds some more complexity. We cannot use it for find, right? Because find returns iterators and we don't have iterators. But maybe we can write a customization point that like invokes the sync with an iterator, not the element. But then this might have like undo the optimization because you have to reconstruct the iterator in each iteration and so on. And then it's a lot easier to make something a range by just providing for each while. So maybe we could allow ranges that only have for each while and don't have iterators, right? Because it's just one function as opposed to writing the iterators. And you can still do a lot of useful algorithms. So we have done that extensively at think-cell. Like we have many ranges that just provide for each while, because you can still do iteration over them, which is what you want. And only when you need more advanced stuff like finds or like actually need the pull model, then we add iterator support. Because this is just so much annoying tedious work to manually build out the state machine. And then, of course, the entire thing doesn't work with the range-based for loop. So stood for each is optimized, but the range-based for loop isn't, which is really unfortunate. So eventually, we will want a language solution for that. So we can use the natural range-based for loop syntax without having to resort to algorithms. Now, one convenience thing I want to talk about is that the common case, you just have a sync that always returns true. And it would be annoying to always have to write return true. So we can make that implicit, right? So if the sync returns void, this means implicit return true. And we can also go one step further and say, oh, this means return true statically, so return true type. So we can at compile time detect whether the sync ever does short circuit. And so the default implementation actually checks the return type of the sync. If the return type is void or true type, then we just invoke the sync unconditionally and don't need the branch to check for early exit because we don't have early exit. And then we just also statically return the true type, and there's a thing where we have to like we want to keep it as the true type so we can chain it properly, but there's some metaprogramming involved in there. And this would be really nice with the control flow operator. This is another proposal by Barry, where you can just do something like Rust's try operator, which handles all of this for you, but it's still stuck in the pipeline. The second optimization builds on this. Because let's go back to std ranges to std. Right? This is the logic. So we do the appropriate reserve, and then we copy it over. But if you have a contiguous range, then we can just call the special append member function, which takes a pointer and a size. And this can then do some mem copy of the result. So this is more efficient. This is more efficient optimization. And this is nice for contiguous ranges, with like a vector, array, string, or span. But many ranges aren't contiguous, but they only have contiguous chunks, right? So a deck of T is logically a linked list of arrays, right? So we have these contiguous blocks in a linked list. So they're not contiguous range, but huge parts of them are contiguous. Or if you concate two vectors, right? The end result is not contiguous because you have two different memory blocks, but like each memory block is contiguous. Similarly, when you have a range of spans and you join them, and also our read file function. It's not a contiguous range, but like it reads into buffer, and the buffer is contiguous, right? So we have contiguous chunks in there. And so some ranges have this natural segmentation into chunks, and it would be really nice if you could just express this and like optimize it accordingly, right? Because then we can do memcopy on the contiguous chunks, even though we can't do memcopy the entire range. And the good news is we already expressed this chunking. We already did that when we customized for each while, right? This is for each while on the join loop, right? We call for each while on each chunk of the join view, right? So if we're joining a range of spans, each of those chunks is contiguous, and we're calling for each while on each contiguous chunk. Similarly, on the read file thing, we're calling for each while on each span we're getting from the buffer. So we naturally expressed these contiguous chunks based on the way we customized for each while. So with a very simple tweak, we can actually have access to that. So if we change our for each while to first call a special chunk member function on the sync, if it exists. And if that one exists, then this means the sync knows how to handle the entire range at once and do a specialized algorithm. And otherwise, we use the customization point, and otherwise, we use the default implementation. And it's crucially that the sync gets to customize first, and then the range. Because maybe the sync knows, oh, this particular kind of range I can actually handle for my particular use case. So the sync knows better than because the sync is the one that actually deals with it. And only then does the range get to pick customization. So we can implement a special sync for string appending. If it only gets a single character, it just calls pushback. But if it takes an entire contiguous range as a chunk, we can call append on this contiguous chunk. And then if we change our ranges to implementation to use for each while with the string appender, we get this optimization essentially for free. Because now, if you call for each while on a joint range of spans with a string appender, after a single level of inlining, join gives you the two nested loops. And the inner for each while is a span that the sync knows how to handle. So this ends up just calling the chunk member function, which does the append of the entire chunk. So just for free, we get the ability to handle contiguous chunks of memory or whatever we want more efficiently. And this is really, really powerful. And so the standard currently uses output iterators, and they're somewhat clunky. You have to like overload operator ++ and operator star, even though you don't really care about that. And you don't have the ability to receive chunks, whereas sinks are just function objects that receive single elements and can optionally opt into chunks. So the standard really should embrace that. Should support the output iterator only like for backwards compatibility and focus on chunks, appenders using chunks and sinks. Because that way we can make so many optimizations just by getting the for each while, just by having the ability to receive contiguous chunks. Now, in our original example, unfortunately, we don't have the ability to use chunks yet. So we've got the read file, which this is big contiguous chunks. This is nice. But when we transform it, we end up with a not contiguous range that contains tiny contiguous chunks. And so when we join that, we have just a bunch of tiny contiguous chunks that's like one character at a time. So yes, we have contiguous chunks, but they're not very big. So this isn't very useful. Now we could rewrite this. Instead of using a transform and a join, we could do a split and a join with. So we take our input range and we split it into ranges at the tab character. And then we've got each segment between the two tabs. And then we join them together with another separator, right? And this will produce the big contiguous chunks after the splitting, and then the separator in between the tabs. And if we don't have any tabs, we will just have an entire thing that is just the entire range because we haven't split it anywhere. And we can make join view propagate this contiguous chunk property. So this is the for each while implementation of join with. It calls for each on each element of the other ones, but then whereas the regular join just has the for each while on the inner one, here we also put in the separator in between two elements. So we can propagate the contiguousness, no problem. However, unfortunately, this example just doesn't work because split requires a forward range where we're having an input range. So it just wouldn't compile. And there's lazy split, which handles input ranges, but because it's lazy, it cannot keep the contiguous chunks property. So we can't directly write the code like this because we're having an input range, and then we can't just split it nilly-willy. However, we are totally fine to handling each contiguous chunk of the file separately if we do that, then we just have the entire contiguous chunk and can just use contiguous chunks algorithms and then join them back together on the upper level. So instead of just having read file, we also need the function read file buffers. And this returns a range of stood spans. And then read file is just this joined together. And then when we implement this in terms of read file buffers, we call a transform that gets each contiguous chunk as a span. We then can process this one using split and join buff. And the end result, we have to join all the buffers back together and pass that to string. And this implementation actually propagates the contiguous chunking property. Because we're dealing with contiguous chunks inside the transform, this is then a range of contiguous chunks, which we join back together into a single range. And this is really efficient. And we actually don't implement read file in terms of read file buffers, because you can implement read file buffers in terms of read file. Like this, you just need a special for each while implementation that only takes the chunks in the sink and forward each chunk as a single element to the underlying range. And this is cannoned. So with generators and chunking, we can write very, very efficient ranges code that deals with entire chunks at a time and doesn't have the iterator output. Any questions at this point? Okay. So let's move to the second problem. So a colleague was working on some SQL-like database, and he wanted some way to describe the schema in a compile-time DSL and then generate the SQL statements to create the database entirely at compile time. So something like this. So you describe a table with some columns, and then you just want to call people create, and this gives you a string that you can pass to SQL to create this table entirely at compile time. Now, there are there's a fundamental C++ limitation we have to deal with first. And this involves the _tcs in there. This is because when you're writing a compile-time function, even though it is const-eval, for example, the arguments aren't const-eval. And this is what Matt ran into, right? So we can call a const express literal on a string literal and pass that to a std array. This works fine. We have a literal, we pass that to a const express function, we use it as a compile-time. But if you put the entire thing inside a const-eval function, then string is no longer a constant expression, so you cannot just use that in an intermediate const-eval functions. So the arguments still aren't const express, even though we are in a const-eval function. And this is just a fundamental way the model works, right? So even though we are doing anything at compile time, we can't instantiate stuff based on arguments within a const-eval function. So the solution is to embed the relevant information that we need in the type of the argument, because the type of the argument, that is a constant expression, even within a const-eval function. And so I call this early compile time versus late compile time. If you put it in the type, you have access to it during early compile time, so within the body, whereas if it's just the value, then you only have it at compile time after you return from the function, but not within the body of the function. And so we need to express all our strings, we need to encode them into the type system so we can use them within a const-eval function. The second problem is pretty straightforward with strings. What's this code? What's the size of ABC? It's 4, because ABC is an array of char, including a null terminator, and it's just an array and just produces 4. So like we need a special type for string literals anyway, so we can use them with ranges code. So we combine both of those problems into literal range. So literal range just encodes the values in the type, right? So it's a template, takes all the values, and now they're encoded in the type. And then we can provide iterators over them. They just populate the global array somewhere, put the values in there, and then we use them. And then we've got like a user-defined literal that takes a string, like a bunch of like technical stuff. But the end result is we've got something where we can call size on a TC string literal, and this actually gives the correct result. And it is encoded in a type system, so this size is a compile-time expression even within a const-eval function. So with that, we can tackle the real problems. So this is essentially what create does. Like this is the pseudocode we want to do. We have our type, which is a string. We have our name, which is a string, and then we want to create type name, right? Put them together, have the end result be a string view, and just use that. Unfortunately, like this doesn't compile, right? Like you can't just add string literals and have a compile time string. And what we really want to do is we just want to use the regular range algorithms, because this is what we're used to, this is the code we write. So what we want to do is something like, okay, so we concat the TC string literals, convert that into a std array, and return the result. And like because we store it in a static const expr, we can return a string view to it, right? Because it's just embedded into the memory. So we just want to write code like this. Now the first problem is two doesn't exist for std arrays because like it takes a range and then it has to put the size of the range in the return type. And like range is a parameter which is not const expr, right? This is the early versus late compile time problem. So this just doesn't work, right? We cannot write a function like this that just instantiates a template based on some property of the argument, right? Like this fundamentally doesn't work. Or does it? Because starting in C++26, it just works. This code compiles. We create a concat of some ranges as in a runtime variable, and we can use its size in a constant expression. And essentially, this is because of relaxation of the rules. As long as you don't access any runtime values, you can use local objects, you can use parameters in compile-time code. And the size of a literal range and the size of the concat view. So the size of the literal range, it just returns something, like it doesn't access any memory variables. And the size of the concat view, it has like a tuple of ranges, and then we want to sum them all together. And if neither one of the sizes actually accesses the element of the tuple, then we don't, at no point do we actually access the runtime value of range. So the entire thing is just a constant expression, and the entire thing just works, right? And this is really weird, but also really cool. Because we can just use compile time properties of our runtime values. And so this code just works, right? We just need to encode that properly in the concept machinery. So we could introduce a concept called const-sized range or something like that, which is a sized range, but we can also just use its size in a compile time expression. Like we just have a runtime reference to a range, and we can const its size, and the resulting thing is a constant expression. And I just check that by instantiating the constant wrapper, which is like a generalized integral constant coming in C++26. And then we can also provide a thing that just, given the type of the range, gives you its size, right? Because we don't actually need to create a range objects. We can just, get a fake reference to it and use it at compile times. So just giving the type of the range, if it's const-sized, we can just get its size. Except we can't do it with decl-val because you cannot call decl-val. I'm planning to bring a paper to that because with the changes, this could just work. Instead, we have to do something a bit more technical, where we have to cheat a bit and call decl-val inside the decl type. And then we pass that into a lambda, encode the return type into the type system, and then get it out of the decl type. Right? I'm going to bring a paper to make this just work, because this is just stupid. But anyways, like we now have dependent types or something, right? For this talk, I'm going to use this helper function, which generalizes this pattern. It just invokes a function with some arguments and then does the same trick, but general. And then we can just say const-size is const-decl-val of std size of the range. So it just invokes std size with a fake reference on range, and then we get the type out of there. Anyways, this is C++26. I had to do that before C++26, which is also possible. It's just more annoying. So what we have is a const-size customization point that you can specialize based on various types. So we say the const-size of a std array type is n. The const-size of any range that gives you an integral constant as the return type for size is the value of that integral constant, and then some machinery to propagate that through, right? So it is possible before. Actually, this is a C++23 feature, I think, even the decl-val stuff, not even 26. But MSVC didn't support that yet, so I had to do some stuff. It's not too interesting. It's just possible. I've written a blog post if you can. But this means that we can implement std ranges too for an array, right? So we take our range, we instantiate the std array by just using the size of the range at compile time because it's context-sized, and then we can do that. And then we just copy the result in there. This implementation just has the downside that std array, this requires a default constructor, right? Because we construct an array, which inherently requires a default constructor. But you can throw a bit more metaprogramming at the problem and generate an initializer list of all the values, and then you have std array. The point is we can make it work. And so we can write code like this, right? To create our object, we just concat the string literals, turn that into a std array, store that somewhere where it lives, and then return that as a string view. This is really nice. And this actually supported, like, this part was supported out of the box. I didn't need to change anything for this use case. It just works because we had this context-per-size concept. However, the colleague didn't write code like this. For starters, we have to like do the spaces, right? This is kind of annoying. So we have concat with as an extension where we just give a separator and then it puts the separator in between. That is not too much of a problem either. It's just appropriately sliced concat where we put the separator in between the ranges. It just works out of the box. I didn't have to change anything. However, my colleague didn't use concat with either because we also have qualifiers that we want to put in there when we create the DB, and the qualifiers might be empty. So my colleague used concat non-empty with, which first filters out all the empty stuff and then concatenates the rest. And concat non-empty with costed me months of my life. Because this was the implementation of concat non-empty with when I started. We take the range separator and all the ranges, and then we call make range. So make range just takes a pack of ranges and turns that into a range. So we can use range algorithms on it. Show the implementation later. We then filter out all the ones that are empty, and then we join them together with a separator. So concat non-empty with isn't implemented in terms of concat, it's implemented in terms of join, just after filtering them out. And this works at runtime. But the entire thing doesn't have a context-per-size, because we just lose the context-per-size information. Even if all the input ranges have context-per-sizes, we just lose the context-per-size information, and then we can't call to array, because we don't have the size anymore. So what you could do is you change the implementation to do some metaprogramming. So we have a pack, we filter out the empty ranges from the pack, and then forward to concat with. And this is the implementation that I just gave my colleague so he could start working. But another colleague was like, yeah, but this is kind of ugly. Can't you make this work? So I spent a lot of time making this work. So let's begin with make range. This was the implementation with make range when I started. So we make range, we just take all the ranges and turn them into std array. So this just turns a pack into range, and then we can iterate on it. However, each element of the resulting range has the same type, because we put them all in a std array, right? Which means that if we have our fancy compile-time-sized literal, the result of make range is a span of const. So I've lost the size information, because they were previously encoded in the type system, but now I just have spans, so I've completely lost the size information. So I need to have a range where we can just keep the individual types, right? And this leads to an implementation of make range that's just make tuple. However, a tuple isn't a range. Because, like, what would the type of the, like, you have an iterator, you index into it, like, what would the type be, right? It's a runtime value, so, like, it would be some kind of variant, right? You can imagine a tuple iterator that returns a variant of all the types, right? But, like, this adds overhead. Like, this is a non-starter. However, what we could do with tuple is we could implement for each while for tuple. Because this one doesn't require iterators. And we just call the sync on each element of the tuple. This doesn't introduce any overhead because we don't need to construct a variant at any point. And this is a concept that we supported in the library, and I call it homogeneous ranges versus heterogeneous generators. So if you have a homogeneous range, we have iterators. So you can use begin and end, and optionally for each while. But if you have a heterogeneous generator, you only have for each while. Homogeneous range, you have a common range value type for all elements. But for a heterogeneous generator, you have potentially a type list of generator output types, right? Because a tuple has multiple output types. This means that you're severely restricted in the algorithm and views you can use, and because you have to essentially use a generic lambda when you iterate our heterogeneous generator, because the lambda is instantiated with different types on each iteration. And so every homogeneous range is a heterogeneous generator, but not vice versa. And tuple is a heterogeneous generator. We can just call for each while on a tuple, give it a templated lambda, and then we do something with each element of the tuple. And we can use like if const expert to select between different types and like handle each type separately. We can also use index sequence. So index sequence is a compile time sequence of 0 to n. We can pass that to for each while, and then we get each index as a compile time value. And this is like an early compile time thing. So we've got the value of the index sequence as an early compile time value and can do fancy metaprogramming with it. Or also, if you want to do metaprogramming on type lists, we give type list for each while, and then we just have a range of type identities, and then we can just use general range views and algorithms to do fancy type-based metaprogramming. And this is how we do most of our metaprogramming. And this is also where Matt comes in. So in his talk yesterday, he wanted to do something like this. So he wrote an emulator for the Z80, and he said, okay, so I've got all the opcodes, and I want to decode each opcode into a function pointer and collect them all in an array. And this isn't valid C++, because we have the opcode, even though as late compile time, so we can't decode it, and then we can't compile it, we can't do it. But with just a couple tweaks, we can instead iterate over make integer sequence. And this gives us the integers from 0 to 256 as a byte, as a constant thing. We can then have the thing in the type system, decode it early, and compile that into function pointer. And we already implemented std ranges to array. So this part just works. And his second implementation, we went ahead and wrote the specialization for the instructions with the PEG expansion. And we can also just use range algorithms. So make integer sequence, we transform each byte into the appropriate function pointer by instantiating the thing at compile time, getting the execute function, turning that into lambda, collecting them all into an array. So this just works if you were using think cell stuff. Other cool stuff we can do. So filter view. This is the for each while implementation of filter view, calls for each while on the base thing, but then skips some elements by not passing them onto the sink. But because we now have different types, we can do stuff like, hey, so is the predicate one of those compile time expressions that doesn't actually require the one-time value of the thing? And then we can skip on it in const_expr code, and so filter based on type information. And because we don't instantiate the sink on the type that weren't taken, we can write code like this. So we can take a tuple, we can filter out keep only the integers and turn that into a std vector. Right? And this just works because the filter just appropriately skips over the types at compile time. And it's really cool. Not really relevant for this example yet, it's just really cool. Anyways, with heterogeneous ranges, it means that we're done with the first step. We have a compile time-sized range with compile time-sized elements in concat non-empty graph. The next step is filter. And with filter, we use compile time-sized information because filter isn't a sized range. Because this would be the size of filter. We just count the element that have a predicate. Unfortunately, this is like a loop, and size has to be 01. No problem, we can do the favorite technically true thing by saying, hey, it has to be const_expr sized. No, it's 01, because it's a compile time-sized range. It's just potentially a big one, right? It's just saying all algorithms on an array are 01 because the size of the array is a compile time-sized constant, right? Technically works, but not nice. We can add another constraint and say, okay, so we're const_expr sized, and the predicate only depends on the type, not on the value. And then this countIf is an O1 that's hopefully optimized because we just add a bunch of true false statically at compile time. But still not quite. And it would help me because I have to do it before C++23. And so I have this variable template and okay, so I specialize my filter view, but then I don't have access to the values. I can't do it. I can't do the countif in there because I don't have the base range to iterate over and I don't have the predicate. So I can't do it. And the reason I can't do it is because it is not actually, these constraints aren't actually enough to properly constrain the compile time size of filter view. Because of something like conditional range. So quick detour. This is code I've shown in an example in another talk where we want to do some range algorithms to reverse all the words in a string. So we start with hello world. The end result is all the words are backwards, but still in the same order. This is done by splitting the range into chunks, then transforming each chunk, and then joining it back together. And the problem with this code is that the transformation either returns the chunk or the reverse chunk. But these are different types, so it doesn't compile. Right? And one easy fix is to eagerly turn them both into std string. And then it works because it's the same return type, but this is an eager allocation. A nicer thing is to return conditional range. This is something we have at thinkcell. It's not in the standard. And essentially, it's just a variant of two ranges, but a variant with iterator support. So you can iterate over one or the other depending on a one-time condition. And conditional range is a problem for filter. Because if we have a tuple of ints, compile time sized, and a tuple of doubles, also compile time sized, we can then create a conditional range based on some random value from the user. And this is a range that's either over this tuple or the other one, but it's still compile-time-sized, because both tuples have the same size. So whatever the runtime value is, we still have the same size. It's just the values are different, and the types. And so if we filter on types, we no longer have a compile-time-sized range. Because if you say, OK, give me only the ints, then the answer is either 0 or 3, depending on the runtime value. Even though we have a compile-time-sized range of compile-time-sized ranges, right? Like we lost the size information after the filter. It was preserved until there, and then we filter, and then we no longer have it. So filter actually is only compile-time-size if the range has a compile-time size, the predicate only depends on types, and we know at compile time each type of the element, so we can at compile time invoke the predicate. And this is where we need to introduce a new concept called tuple generators. So a tuple generator is a type that is a generator, so we have for each while. It is compile time sized, and we give it the tuple interface. So we can get each element given a compile time sized index and can decal type that. And if you have a tuple-like generator, most views are themselves tuple-like generator. And the tuple generator is essentially the random access equivalent of a generator range, right? Because we have random access, not just the Bush model. And so this leads to this thing where we have generators. You can iterate over them with for each while. If you have a tuple generator, you can iterate over it with the upcoming template for, because template for essentially invokes get a whole bunch. And if you have a regular range, use the regular for loop. And with tuple generators, we can finally make our filter view compile time sized. Because what we're essentially just doing, we get all the elements, we decal type the thing, pass that to the predicate, and then count that all up. And this is an entirely compile time sized expression now that just does some work at compile time to count all the types out there. And this took me a while. But anyways, with this simple code, your filter view is now compile time sized. And while we're at it, we can now also implement get for filter view. So we essentially can give filter view random access, provided the random access happens at compile time, so the constant. Because we just need to do some index translation from the outer index to the base range index, where we just count our skipped elements, which we can do because the predicate works at compile time, and so we can statically skip over the elements. And this means that at this step, we have compile time sized range with compile time sized elements. Because the filter only depends on the type, because it was compile time sized, so we get all the information, and so only the join width left. And for simplicity, I'm just going to consider join. Join width is essentially the same, it's just we have to add them the separate. So previously, this was the implementation of join with size. So if you're having a sized outer range, and each inner element of the range has the same const x by size. So if you're having a join of like a range of stud arrays of size 3, then we can make join view compile time sized by just taking, or sized in general, by just taking the size of the outer range and multiplying it with a constant. Right? If they have different sizes, we have to add them all up. But if we know at compile time they all have the same size, we can just add them, multiply them together. But this isn't what we have. Right? In our case, we have different sizes of each of the ranges, because the ranges that we pass into concat non-empty, they have different sizes, and we just know they're all non-empty. So we can't do this implementation. But we can do something with tuple ranges. So if we don't have the same const x per size, but we're having a tuple generator, then we can get a pack, get each element, and sum all their sizes in a fault expression. And this doesn't involve a loop. So it's a 1, because we're just adding all the sizes of each individual element essentially at compile time. So now we're having a compile time sized. But at this point, when I wrote this, I had a bit of a déjà vu. Because I wrote very similar code just a couple of days ago. So in particular, the tuple case for join. I wrote this code a couple of days ago in concat. The size of concat is just the size of each element in the concat tuple. So concat range of ranges stored as a tuple, and we just sum all the sizes. And this is what we're doing here too. And the join for tuple, it's the loop over the outer range with the loop over the element range. And the for each while for concat is the loop over the tuple and then the loop after each element. Because ranges are tuple, we can just implement both with for each while. So a concat is really just a join of a tuple. Because with join, we take a range of ranges, we join them together. With a concat, we take a pack of ranges stored as a tuple, join them together, but the tuple is now a range, so concat is just a join of a tuple. And that's in fact how I changed the implementation of concat. So concat just delegates to join. And then we have various specializations of joint view depending on the power of the underlying range, because concrete view has slightly different properties. So we need a special case in some cases. But the base case, where we're only having generators, not iterators, it's the same for both join and concrete, because concrete is just a join of a tuple. And with that, I was finally done. And I could replace this ugly metaprogramming code with this nice ranges code that just works at compile time, produces the compile time-sized ranges with all the essential power. And this, the upper code and the lower code, they are the same algorithm, right? And I don't mean that, oh, they're isomorphic. I mean, they're literally the same algorithm. Because what our compile time-sized filter and our compile time-sized join do, essentially, is exactly this metaprogramming code just internally. It has to skip over elements at compile time. It has to do all the logic. And the end result is a join of a tuple, which is a concat. And so this is just the same code. And this means that my colleague who said, you shouldn't write this code, you should write this code, was absolutely right. Because after a bunch of library infrastructure updates, the actual code to make concat non-empty with work was just this. And that's really cool. Like, it just fell out of the pipeline, and then you can't just use it at compile time and have it done really nicely. Anyways, we sell a PowerPoint plugin. Okay, I'm going to defer questions to the end, because now it's time for some standardese lawyering. Entirely different. So this is some code that finds the smallest Fibonacci number that's greater than some threshold. So we start with a sequence of infinite integers, then we transform them with the Fibonacci function, which just computes the n Fibonacci number, and then we just have all the Fibonacci numbers, and now they're sorted, and we want to find the first one that's smaller than a given value. And so we just use phi-diff. And this is also some code I gave you in some other talk. Now there's just a slight problem with this code. If we carefully read the range requirements in the standard, the standard says a range is an iterator of the sentinel that designates the beginning and end. And this is done by having this IS, where like if I is equal to S, then the range is empty. Otherwise, we have all the steps you reach by incrementing until you reach the sentinel, right? This is what a range is. And we say a sentinel is reachable if and only if there's a finite sequence of applications of ++i that make I equal to S. Finite sequence, right? So if you use iota, unbounded, it gives you an infinite sequence of integers, so we'll never reach the sentinel, right? It's not, the sentinel is not reachable, and this is encoded because the type of S is in fact unreachable sentinel. So it is not a reachable sentinel. So far so good. However, there's this other clause that says if S is reachable from IS denotes a valid range. The result of the application of library functions to invalid ranges is undefined. Oh, this means that this code is undefined behavior. We're having an invalid range, we're calling a library function on it. It's invalid because it's infinite, undefined behavior. This code is undefined behavior. We're having an infinite range, we're calling take on it. This makes it a finite range, but take is a standard library function, undefined behavior. This code, undefined behavior. We're calling a standard library function dot begin on iota view. This is undefined behavior. It's an invalid range. This code, UB, we're calling the destructor of iota view, undefined behavior. So we took a poll when this was discovered in Hagenberg in March at the standardization meeting, and essentially we said the standard library should not provide facilities that only cause undefined behavior. And this passed. Like the actual poll had like slightly different wording. So how to fix it? Like how to change this wording to make this, because we have iota view. You're supposed to use iota view. Like it's kind of bad that this is undefined behavior. So let's explore the problem space. We're having two invalid ranges, like code like this. So if you have a subrange of an array plus 10 to array, that is just a true invalid range, don't do that. If you have a subrange of vec1 begin and vec2 dot end, that is an invalid range, don't do that. So these ones should stay illegal. Then we're having two infinite ranges. Repeat 42, just repeats 42 forever. Iota of unsigned 0, just keeps incrementing the iterator, wraps around, go over forever, true infinite range. And then we have ranges where dot end lies, like iota of int, because eventually you will have integer overflow, so, which is undefined behavior for int. So iota isn't really an infinite range. It's just we pretend it is an infinite range by returning unreachable sentinel. Likewise, if you just have a pointer, And you can construct a subrange manually out of this pointer and the unreachable sentinel and just realize like, trust me, I will only iterate as much as is valid, right? And these aren't really infinite ranges, it's just like end candleize. And then we have ranges where we don't know. iStream reads characters from a string. Is this an infinite range? Is it a finite range? Depends on the stream. So generator, it type erases the entire range, so we don't know how the size, the infiniteness. And so what even is infinity, right? Like this is an infinite range. Repeat 42, this will print 42 forever. Is this an infinite range? I mean, surely eventually the user will stop typing, right? But what about this one? So this is a range where the range is done when the dice roll is 6. Like if you're really unlucky, right, the range is never done. And then we have to consider between like infinite usage and finite usage. So with infinite usage, you just, for example, a server, take some input, process it, writes it out. And you just keep going forever, because the server runs forever. Whereas if you combine like IOTA with like something that is finite, or in our findef example, we're only looking at a finite prefix because eventually the other range is exhausted or we find a condition that we care about. So here we're having infinite ranges, but we don't really use them to infinity. We just use them for finite. Like for all of those, we could provide an upper bound, but we're just too lazy to write one. So we have the unbounded IOTA. So let's come up with some definitions. So let's say we have an infinity sentinel, where no matter how many times you do plus I, you will not encounter undefined behavior, and I equals S is false. And these are the true infinite ranges. Repeat, IOTA of unsigned, potentially iStream, potentially the generator, depending on what you're doing. However, this is not IOTA of int, this is not the pointer of the unreachable sentinel, and the two broken ranges. So this captures half of the thing. For the second case, we need to talk about maybe like unbounded sentinel. So whereas an infinite sentinel is never reached, an unbounded sentinel is I equals S is still false, but eventually you will encounter undefined behavior. So the range is still finite, we just don't know. So we have an infinite, we represent it as an infinite range, but there's only a finite prefix that is actually usable, it's just not determined a priori. And this is the IOTA of an int, right? You can only increment it like int max times before you encounter undefined behavior. So this is not infinite, it's just unbounded. Similarly for the subrange, and potentially for the std generator. The problem with this definition is that it is too broad, because it also allows the subrange area plus 10 plus array. This is an unbounded sentinel where you can increment it 0 times. And this would make it a valid range, right? Similarly, the vec1 begin to vec2 end. You can increment it until you reach the end of vec1, and then you have undefined behavior, and then you should stop, right? And in general, we've just made any iterator sentinel pair where we can compare the two a valid range, which is bad because we still want to reject those things. Like we want to have asserts in the subrange constructor that like, hey, you're having vectors of 2 different iterators. What are you doing, right? So this definition is too broad. So maybe we make it stricter and say, okay, so we're having still the same semantics for unbounded and sentinel, but only the sentinel type unreachable sentinel T makes it valid. So IOTA works and the subrange, but not subrange the true infinite ranges, because we're not using the unreachable sentinel T, right? This is good. But we've also like don't allow now a std generator that is the infinite or finite, because it doesn't have unreachable sentinel T. It just has some other type. But like, do we really care about generators? Like, is there a difference from the ranges machinery between the infinite range and the unbounded range that has undefined behavior after 10 iterations? Or is it merely just an implementation detail of the generator and the range algorithms don't need to care, right? Like, I don't have answers in this space. Like, this is just me talking out loud about trying to fix this problem. And even if you decide this one, what about the difference type? After we did plus I an infinite number of times, I minus begin does not fit in a pointer diff T. Right? Do we care? Like for finite usage, it doesn't matter because we're constrained by something else. But if you're having an infinite usage, maybe you have an iterator from like way back then, and then you just waited a couple hours and now your iterator is all the way over there and the distance is no longer representable. But also, this isn't really a new problem because pointer diff T on a 32-bit system is like only 2 gigabytes, and you can reasonably have ranges that are bigger than 2 gigabytes on a 32-bit system, right? So this problem was always there, it just hasn't been properly specified until now. Now, IOTA view of unsigned is interesting because it like wraps around. So if the beginning is 0 and the current iterator is 4, what is the difference? 4, unit max plus 4, 10 times unit max plus 4. All of those could be like valid answers for the difference because it wraps around and we don't know how many times it wrapped around. Like we probably want to say, oh, the difference is always like the smallest one and for cyclic ranges. But this also has to be specified. And right now the standard just ignores that. And so once we did all that, then we want to have like a new sizing hierarchy. So where we have sized ranges with a known finite size, infinite ranges, which are the true infinite ranges where we know they're infinite, and then just all the other ranges where they could be finite, infinite, or unbounded, and we just don't know statically. And then we can do stuff like this. So in C++26, we will have parallel range algorithms. So you can say, I want to do a parallel transform, and this is the binary transform that takes 2 ranges and invokes the function with 1 element from each. And right now, this example doesn't compile because transform, the parallel one, requires that both ranges are sized. And iota of unsigned is an infinite unsized range, so this is rejected. But it's kind of stupid that this is rejected because we just picked the size of the other range because the iota one is clearly bigger, right? And this actually motivated me to work on this problem. Because we can just say, okay, they're either both sized or one is sized and the other one is infinite, and then it just also works. We can do optimization. So we have an infinite range and we take 10 elements. Take does a bounds check. Every iteration does a check, hey, have we exhausted the underlying range? But if it's infinite, we can omit that bounds check. And in fact, there's going to be an unchecked take in the pipeline anyway, where you know that you're bigger than 10. And so I wrote a paper to propose this. And while this paper was discussed, I thought, oh, I'm just going to introduce a new concept, infinite range, and then we can relax the wording in those cases. Somebody pointed out that infinite ranges are actually undefined behavior, and maybe we should tackle that first. And this made everybody really sad, especially me, because now I'm stuck to solving this problem, which is not what I anticipated when I wrote this paper. So coming to a C++ standard library in the next decade, less undefined behavior than using the damn. So to conclude, what should definitely be included in stored ranges? Conditional range. It's a small helper. We're going to have any view, conditional range fits right in there, just useful, should be included. The for each while customization point is desperately needed. It's just a hidden optimization that makes range algorithms usable in so many cases. Similarly, we can then build sync-based appenders on top of those and have better output iterators and better performance and can do express chunking when we copy stuff around. We also already have compile-time-sized ranges. Thanks to the C++23 semantic changes, we just need a concept for it, and then we can also add stored ranges to stored array, because that is useful in some situations. And we definitely want a fix for infinite ranges, but like that's not really important because like in practice it's fine. Like this is just the standard library specification is clearly broken. However, the pure generators, and especially the heterogeneous generators, are probably not a good fit, right? They're like a wild departure from the existing range concepts. They don't have iterators, you can't use the regular for loop, and the heterogeneous ones don't even have a single value type. Like having tuples as ranges is nice, but it's like not really, like it requires a lot of work, requires a lot of specification. It's probably not worth it. And especially because with reflection, we can somewhat emulate them by instead of having a range of types, we can have a range of stored meta infos representing types. So the nice thing about reflection is that the meta info can represent anything, it's completely untyped, and so you can just put them in containers, you can use range algorithms with them. It's just a bit more of a clunky interface than having the type directly. So anyways, if you want to work on any of that, proposals are welcome. The study group for ranges, I'd say we are like really small, like really nice, really welcoming, really good at spotting weird edge cases you've completely missed in your paper, but you know, we do that in a very nice and friendly way. So if you want to work on any of that in the space, I welcome any help. If you also like working in PowerPoint plugins that don't involve crazy metaprogramming, we are also hiring. So if you just want to use our range machinery, we're hiring, and thank you.